Good morning, Irvine. Another happy day. Start of the midweek, right? The excitement builds. We're going to see a lot of interesting physics this morning for our start to the day. The adrenaline. No high voltages today, so no concerns about any real big sparks, but let's have a low spark here today. All right, so today's theme, if you look at it here, today's theme song is going to be "You Light Up My Life." Right? So that's what we're going to do here, is light up your lives with the stuff we're doing today. To do that, I think we need some power to start with, don't we? And power is a useful commodity for us. We've learned that power is the rate of change of energy. So electrical power so we have the rate at which work is done, or the rate at which the total energy changes, or the potential energy. We take it, the power is the rate at which the energy is changing, going to do some task for us. So in resistors, what we're doing is putting a current into some resistor, and we think of it, remember, something like, what did we use for the symbol? Eta times the length divided by the area. So for the resistor, when we put some current into it, resistors do not store charge. So the charge that goes in one end is coming out the other, and the current that we're seeing here is dq dt, right? The rate at which the charge is flowing through that circuit. So the resistor is just some object where there's some frictional loss going on with it. So this is a frictional loss term. Frictional loss occurs so when we start somewhere, going through a resistor, for example, we might be at some energy level. Then as the friction dissipates the energy we've got, what happens to it? It goes off as heat, as we discussed. So if we're at some voltage that's a voltage that's higher here, and so it's at some voltage there, and it's at a reduced voltage on the other side, there's a drop in voltage, a delta V, okay? There's a delta V across the resistor. So that delta V across the resistor means the energy per charge changed. Voltage, energy per unit charge. So the energy per unit charge changed. That energy went into the frictional loss, the heating. The energy was the amount of charge that's moved times the voltage. That's the total energy that's available. The rate at which the energy is changing is the power, and that's then equal to the time rate of change of that energy that we collected. Now let's think about it just a little more to make sure we have the interpretation right. If we have a voltage, V, which is the energy per charge, and then we move Q charges, a total amount of charge of Q across that voltage, then we have done this much work. We have changed the energy of the charges by this much. And this is the amount of charge over time that we moved across that voltage. So that's the time collected total energy. This is the time rate of change of the energy. Each element of charge is being added how often? And if the voltage stays the same, if the voltage drop that we're considering doesn't change, then this is just the voltage times dq dt. And dq dt is the current. So this is V times I. So the power is IV. I guess sometimes people like to use capital IV, right? Or if you replace V, you have, using V equals IR, you have three different possibilities of the way you can write this. Providing that Ohm's law applies, providing V equals IR, you have these different expressions for the power. If that is not a reasonable approximation for Ohm's law, then you have to be careful to calculate the power from first principles like we were just talking about. Okay, so this is then called the ohmic dissipation, the Joule heating, if you will, for a resistor. So this is Joule heating power. So that if you call it Joule heating, it gives you a conceptual handle, heat. So that it's saying that the resistor is dissipating the directed kinetic energy of the electrons into thermal energy, heat. There is, however, a cautionary note to add for this, and it's not typically in your textbooks. This is the energy that's available in the electrons. When they've been accelerated across a voltage V, total charge Q, then that's the energy that's there. This doesn't say where that energy gets dissipated. So you have to be careful when you're doing a calculation of saying, oh, the power in the circuit is so much. We can have power, we can have that directed kinetic energy in the circuit. This calculation is when it's being dissipated in a resistor. So you have to ask, okay, was there a mechanism for the dissipation? We've got charge flowing in the circuit. We know we got it up to a voltage V. We know we stored that energy in the circuit. It doesn't mean it's dissipated unless it's done there in the resistor. So you have to find the resistive place and look for where the energy is turned to thermal energy when you do this stuff. Okay, so now let's consider this as a function of time. I've given a picture here where you probably are considering it as fairly constant in time. Constant current, so constant Joule heating, constant I squared R loss. What happens if time dependence? What about time dependence? So time changing, right? Time changing voltages, currents, and so on. What about that? For example, what happens if the voltage across a resistor looks something like this? Now we have, and let's say that there is a zero here. Now the voltage is, in this drawing, say positive right at the start there on the first vertical axis point, and then it's dropping down, going through zero, coming back up, and going back and forth. And in addition then to hearing nature's voice, you're seeing signs, right? So this is a moment where you see signs. And we could say, well, let's see. If we wanted to have this be t equals 0, what trigonometric function would we use for this one? We could use cosine, because that's the easiest one to come to mind. We could use sine if we wanted to, but then we have to add a constant in the in the argument, right? And that would be a 90-degree shift. So if we looked at this one and said that it was going as V max times cosine omega t, and omega is 2 pi f, 2 pi over tau, the period. So the frequency f commonly in the United States, f is 60 cycles commonly in the US for household power. Household power commonly 60 cycles per second, 60 hertz, we would say. So at 60 cycles per second, you can hear a hum that's at 60 cycles per second. So there's something loose in the wires, and there's enough magnetic force involved somewhere to move the wires. Then you'll hear a little hum at 60 cycles. But your eye doesn't really see it very much for a lot of phenomena. So for example, yesterday's demonstration with the Jacob's ladder that had, it was going on and off. The voltage was going like that. But the result of the arc that you saw, your eye didn't see it. But we could see it on the piece of paper for the few of us who were down here and looked at that when I stroked the paper through the arc. Okay, so at 60 hertz then, let's look at the power that's being dissipated here. What is this? Well, here's a voltage maximum. So at that same point then, if we were to make a graph of power dissipated in a resistor. So this is dissipated in a resistor. The power dissipated now, let's see. I've got a big voltage here, so I've got big power. Now I go along here and the voltage goes to 0. Voltage goes to 0. What is the power dissipated in the resistor if the voltage is 0? 0. So I'm going to have that guy is 0. Now the voltage is going negative here. Oh, negative power, negative friction. Does that happen? Oh, okay. So what this means, the voltage is negative, means the current got turned around in the resistor. The current's being driven the other way. So instead of having V equals 0 on the right and V equal V over on the left, they're flipped. It's a mirror image. So the current is going one way at the start, and then when we cross that 0, the current turns back around and goes the other direction. And, oh, so it's going the other direction, but making friction, so it reaches a max here. So it goes like this. There's the power that's dissipated in the resistor. So let's put in the resistor. Okay, cool. Or hot is a hot topic. Well, let's see now. That means that if you had a 60 cycle current, it's going this way, back, this way, back, this way, back. It means that even though the power station is providing the energy for it, the electrons that are doing the movement through that resistor don't move very far. They don't come from the power station. They're in the wire, they get pushed to the left, pushed to the right, stand up, sit down, and they fight, fight, fight right there with just making friction locally. So this is cool. You get the power transmitted all the way down the line, but the electrons that you're using don't actually move very far while you're using them. The power, okay, and then the energy. Remember, the energy is equal to the integral of the power times the time. Oh, it's over there, right? du equals p dt. So if I start thinking about looking at the power here, and I look at, isn't this the area under the curve? And doesn't that represent u? Right? So the area under the curve is u. Now let's just take a look at this picture. Here's the maximum power that's dissipated. Okay. Physics is a little difficult, isn't it? And so sometimes you want to change your perspective on it. Sometimes you'd say, this stuff is so hard it stands me on my head. And didn't we have somebody who helped do that? Right? So he's already got, I believe it was Val, right? So Val stood on his head. I want you to think the same way here. Just take your head and kind of go like this and look at it, upside down. Doesn't it look like the area that's hatched equals the area that's unhatched? It's the same picture, just upside down, isn't it? So if I want to know the area of the hatched part, oh, I have also then answered the area of the unhatched part. And if I have those two are equal, that means each one of them is half the total area. And if I look at that, what is the shape overall of the total area? That's a rectangle. Isn't a rectangle a whole lot easier to calculate the area than some snake? Right? Length times width, height, voltage, power max times how long, and divide by 2. Divide by 2. So if you do that, it says that the energy is half of the maximum power times the time it was on. So you can talk then about the power averaged. Let's just be careful about this. Suppose that I asked you, or you asked yourself, what's the energy delivered in the time period that's between my hands here? Now that has mostly hatched area, right? So it's got the maximum there. What about looking at it right here? It's almost all blank and there's no power. So this idea of the power is half of the total is when you've averaged over many periods. Now at 60 cycles per second, it doesn't take long to average over many periods, right? So it's pretty common to do that. And so we would say that the power, the average power, this is averaged over time, average over many periods, equals 1/2 of the max. So the way we talk about this is, you might have heard people talk about RMS. RMS values. That means root mean square. So when we look at 1/2 V max squared over R, oh, doesn't it look like I have to do a V max? Watch this. V max over square root 2, V max over square root 2, all over R. Isn't that the same thing? So we write that as V root mean square. And we talk about the power then according to the RMS voltage. So the RMS voltage, let's take a look here, get ourselves a little understanding. Here's the voltage again, going like this, versus time. There's V max, and VRMS is V max over square root of 2, which is V max over 1.414, which is about 0.707 V max. So we could talk then, if we knew it was a sinusoidal function, we could talk about the voltage and the power in terms of the maximum value. We could talk about the average value like this, the RMS value. We could talk about the time-dependent one exactly as time goes along. You pick for your purposes. When you turn on the light in the room, you get 60 cycles per second, means you have 3,600 cycles per minute. Then you might as well just think about the average power. You don't care about the time-dependent part too much. And so you're just going to talk about half of P max, but instead of half P max, we just talk about the RMS power and the RMS voltage. When you go over and stick something in the wall, the RMS voltage is typically about 120 volts in the US. 120 volts at 60 cycles per second. That means the V max at the wall is about 165, 170 volts typically. Higher than the 120 you're talking about. But in terms of power delivery, which is, well, after all, power over time is energy, and energy is what you pay for. The rate at which money is leaving your wallet equals power. The total money which has left your wallet is you. Okay? That's where your money goes. You can have stuff coming in, food calories, right? Which you, again, paid money for the energy, right? So money is apparently an equivalent or a useful in-betweener for getting energy. Okay, so let's see, 110 volts makes the light. Let's take a look. We have an old style light bulb here. Let's take a look at this. Yeah, pretty good. Let's do it without even putting the screen down, maybe. That's not quite so bad. Okay, let's try some ligates. Oh, that's better. Remember we went green last time we tried that? Okay, so there was a light bulb. I'm going to turn on the current to it, and this is an old style light bulb. So it has a filament, probably a tungsten filament, and there's a picture over on the right. Who's that a picture of? Thomas Edison. Who invented the light bulb? You want to say Thomas Edison, don't you? Well, Thomas Edison wanted you to say Thomas Edison too, real bad, and he was very good at it. Okay. Earlier people, there were hundreds, I believe, literally hundreds of people working on light bulbs. And outside the US, I believe that credit generally goes most dominantly to a person whose last name was Swan. So as you notice here, Edison has a dominant perspective on these things in the US, even with the power companies, Southern California Edison, right? Which operates under the general principle that was espoused by Westinghouse and Tesla, not Edison. Edison's power ideas were not adopted in the US. Anyway, this guy was an incredibly brilliant guy, worked day and night by all accounts, and had lots and lots of brilliant ideas. I'm in the dark here, but that guy was incredibly brilliant. And what did he do? Let's see. Didn't he more or less invent the motion picture industry? With the camera, I think, for that. All kinds of things. The phonograph, I think he played a role in making phonographic records. Just unbelievably creative continuously in his life. And very successful in getting things applied to business applications for social utility. Very skilled on the business and engineering side. Okay, let's take a look at this. This is an old style light bulb, of which there are still many in use, that has a tungsten filament. And that tungsten filament is very low resistance at room temperature, but then when we put some voltage onto it, now what do you see? This is lower voltage. Can you see the orange glow? So there's at very low voltage, the V across the filament is not very big right now. In terms of RMS voltages, it's probably about 30 volts right now. So at about 30 volts for this particular filament, it's starting to get hot enough to glow in the sort of dull orange, dull red kind of color. Let's see if we can make it a little darker even. Can you still see it okay? And at this kind of level, which is lower, what color would you ascribe to that now? It's a darker, kind of dark cherry red, isn't it? And then as I go back up to where I was, now it's kind of a pretty orange. What's the shape of this filament? Can you guess from looking at that two-dimensional image? Okay, so I'm going to make it a little brighter and then turn it around in different perspectives for you. Oh, look at that. As I raise the voltage, the color is getting a little more yellow there. Okay, let's take a look. So now if I rotate, bring it around, can you get some idea of the shape that's involved? It's a loop. I think that's a fair enough description. Right? There's two leads down at the bottom, one end of the tungsten going up, going through a loop, coming back down, the other end attached down below to these pieces of wire which come through the glass that's there. Now, why don't we just have the bare filament? Why do we have the glass around there in the first place?
You keep it hot.
Uh-oh. That's curious. We went green for a little while there. We must have been doing something right, protecting the environment. Okay, so the glass protects the filament from anybody touching it. And when something is glowing hot, you know, that would be bad news, right? Another thing that the glass does is it allows a different environment around the filament for the filament's purposes. If you heat something up really hot, commonly things burn, don't they? Or they oxidize. They change their property by interacting with the gas around them. So if you took a light bulb and you filled it with argon instead of air, then argon is very inert. It doesn't do much in the way of chemical reactions with things. And if you heat the filament up, you're going to not oxidize its surface, and it'll last a long time. So the glass bulb serves several purposes. And then, as we said last time, the bulb is made large enough so that whatever the heat load coming out in radiation from it doesn't melt the glass, causing it to form a heap at the bottom. Okay, now we'll turn it up a little more. And what are we seeing? More and more light saturating the sensors in that camera. So if I'm turning this up, is there any doubt that the bulb is getting hotter? So at some point I probably wouldn't want to touch there. But, oh, look at that. If I put my hand right there near it, I can feel the heat. I can feel the radiation, the electromagnetic radiation of the visible light and infrared light hitting the back of my hand. So this frictional loss of the Joule heating in the resistor is causing electromagnetic radiation from this tungsten filament. Turn it up more. The color gets more yellow and then heading towards, oh, I'm going to go all the way. That's as far as it'll go. That's pretty bright, isn't it? Okay. So you get your color spectrum on a tungsten filament. Tungsten has a wonderful property that when heated up pretty well, it gives a fairly broad spectrum with lots and lots of spectral components. Gets pretty close to white light. It's very close to sunlight. So I love the tungsten bulb era. Now, you guys are starting to live in a different era. This light, most of the radiation in the Joule heating is coming out as infrared, and you can't use it for seeing because you don't see in the infrared. So this is a fairly inefficient light bulb, although it provides a light spectrum that I really enjoy. So the sort of more modern light bulbs use Now we're heading towards light-emitting diodes and things of that sort that have a little more efficient emission in the visible and less heating. Well, not zero, but less heating.
I have a question.
Yes, ma'am.
So does the lower voltage correlate with the higher wavelength?
Lower voltage will mean that the peak in the wavelength is longer. If the bulb is cooler, the peak of the energy spectrum is shifted more and more towards the infrared. So the black body radiation that we're seeing here, the peak depends on how hot. As we made it hotter and hotter, the peak of the radiation was shifting into the visible. Hence, you saw more of the full spectrum in a whiter light. Oh, the excitement, the excitement. Okay, let's go back to here. Any other questions? Any bright ideas go off here? You could, what's this guy's last name? Edison. It must have been son of Ed, right? Okay. Well, that's what that means. Okay. Let's get that guy. We got them all back on? I guess pretty much. Okay. Resistors in series. Let's draw some resistors that are in series. In seriatim, if something is done in serial, if you're watching a series, right, then things happen one after the other. So we have R1, R2, R3. Now let's take a look at this, and let's let nature talk to us and say, what is the equivalent resistance? I have these three resistors that happen to be in a line. They're in series. What is the total resistance? The equivalent. If I wanted to say R equivalent equals, and then put something on the other side, equation equals. Got to have an equal sign in there. So if we want to do that, let's see, resistance. We're going to remember that resistance was eta times the length divided by the area. I've got this first resistor here. It has some length and some area. If I put a second resistor down below, doesn't that increase the length? Suppose I have the same area for both of these resistors. If I put one here and one here, then the length factor changed. It became L1 plus L2 if the area stayed the same. So what that tells me is if I do the work to go through this resistor, then I'm going to do the work to go through this resistor, then I'm going to do the work to go through the third resistor, and it's the equivalent of additional lengths going on. And so R equivalent is R1 plus R2 plus R3. So it's the sum over n's, right? N equal 1 to n of R sub n, right? That's the physics that drives it. Now you can think of it with some math if you want. You can say, oh, the total voltage is here to here to here, and the current that flows comes in. If you put a current, it's going to go through each one on out the end. So you know the current, dq dt, is the same through each of them. And then you can write your math equation for going across the voltage totals. Voltage total is going to be I times R equivalent. If we wanted, going all the way from here to here, the voltage total is I times R equivalent, and that has to be equal to I times R1, which is V1 plus V2 plus V3, right? So I times R2 plus I times R3. So it's the same statement that we just had, yeah.
Did you say that I stays the same?
The current stays the same. Here's the physics of it. We say the resistor can cause a frictional loss, but resistors do not store charge. So the charge going in one end of a resistor is pushing the same amount of charge out the other end. So the charge is not getting stuck anywhere, not being stored anywhere. So the current must be the same through all three resistors in this example.
But not potential difference, right?
But not the potential difference across them. The potential drop across each one is V1, V2, V3, and each of those is I times R1, I times R2, I times R3. But we know that the total voltage drop is equal to whatever the full drop was. So you don't have to memorize some kind of formula. You just have to think about what does the concept of resistance mean, and it will tell you here. Okay, now let's look at resistors in parallel. Let's have another thought in parallel. Parallel is this kind of nifty word because right there in the middle of it is practically the symbol you're thinking of, right? So it helps you in the understanding. Parallel resistors, let's do something like this. So we have R1 and R2, and the current that goes in comes out the bottom, and there's a voltage across the whole thing, right? So there's a voltage across here. Let's do the physics of it and think about what really happens here. Imagine you're going to take a break and you're going to go out and have an iced tea. You want to have an iced tea and you're going to use a straw. So you put a straw in. You go, and you drink some of the iced tea. You had to drop the pressure inside your mouth a little bit to get the atmosphere to push the tea up the straw to you. So you had to do a little bit of work, didn't you? To change the MGH of the tea and be able to drink it. Most people use straws to bring fluid up, right? If you put a straw on the bottom of the tea and had it underneath, what's going to happen? You're going to get wet, right? So I'm thinking about pulling it against gravity, okay? So now you've got your straw and you're drinking your tea and you say, well, it's such a hot day. After all, it's late August. So I want a second straw. Now you get a second straw. You have two choices about how to use it. You could put one above the other, and now you've doubled the length of your straw. Did that allow you to drink more for the same? Oh no, you had to, that's the series, isn't it? Instead, you would take the two straws, put them next to each other, and then, right? And now what happens with the two straws? What is the equivalent area? The area doubled, didn't it? The area doubled. The length of each straw was the same because you got them from the same place, but the area now was twice as much. And we think back over here, it's the area down below. It's down below. And so what happens here is 1 over the equivalent resistance is 1 over the sum of 1 over the individual resistances. And then you can write your math equations if you want to have another way of seeing it. Take the current. The current that comes in at the top now, just like with the straw, the fluid gets shared in the two straws. Now the current goes to both resistors. But how much current? They don't each get I. we only have so many charges per second entering at the top. Those charges per second are shared between the two resistors and then come out the bottom so that the total flow is I. It's not that there's I in each leg here. It's shared. Now let's think if we had two different straws and they weren't the same. If one of them had a much bigger area than the other, it would carry a lot more current, wouldn't it? So if we look over here, if the resistances are different, the one that has the lower resistance will carry more of the current. You see this sometimes when a stream divides going down a waterfall area or a babbling brook kind of thing, and there'll be one area that carries a lot of the water and another area carries just a little bit. So the flow of the current doesn't have to uniformly divide at all. It will divide according to finding the path that's easiest. Okay, we got a lot through there, but we'll send a little over here. So you get these kind of comparisons here. So it is often the case that you will have some electrical circuit of some kind, and you need a particular resistance value. But you go over to the supply and you don't have that value there. So what you do is decide to use parallel or series combinations to arrive at the resistance you need for your circuit. We're going to show some examples here. Another thing that happens a lot of times is you deliberately do want a circuit that has a bunch of resistors in a line. For example, holiday lights, commonly used on a Christmas tree type of stuff, right? Or out on the decorative stuff people put up on their houses and things. Those have bulb, 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 bulb. Or look at the lights we have up above. One switch turned on all of one type of these lights that are above us. Now, let's imagine that those lights above us are wired in series, okay? We got our light bulbs up there. Let's think about the strip of them that's right above the blackboard, chalkboard. That's a green board, isn't it? Must be energy efficient. So the light bulbs up there, if they were in series and one of them burns out, what does it mean to burn out? It means that that tungsten filament or the equivalent in it got severed, cut. It's called an open circuit after that point. And what that means is if we slice the wire somewhere here, what happens to the current? It stops. It goes to, that's a good word. It's over, right? So when that stops, what happens to the light that was generated at each of the resistors? It's over. So would it be smart to wire that light in series there? No. So those lights are wired in parallel, and that has two functions that are really nice then. If you wire your lights in parallel for overhead lighting, they all have the same voltage applied to them all the time. So if they're all designed to be 120 volt lights, then you've got 120 volts at every bulb all the time. And then suppose that this one burns out. Still the current can flow in through the remaining ones. And so the light stays on to the degree that the bulbs are not burned out. Yeah?
So when is it useful to use in series?
When is it useful to use in series? One place where it's very useful to use in series is Christmas tree light bulbs. Because you buy them at the hardware store, they work for about an hour and a half to 2 hours, then one of them burns out, the whole string goes dead, you go back to the hardware store and buy another one for next year. Hey, smart business, huh? Doesn't that make you think of printer ink? Oh, sorry. Ah, good. Okay, let's take a look at some examples of lights now in series and parallel. Let's see, who would like to, we got, this guy? You volunteered before?
Which one was it?
I don't remember that. Come on up here.
Yeah, that's right.
Watch this. Why don't you just come on up with me? Hi, I'm Roger. Okay, here we go. Let's see now. Series. Let's start down there on the series. What do you see here? Just describe what do you see.
Series of light bulbs, 4 of them,
Okay.
on a glass.
And does it now that you see that they are in a series visually here, and you said it was Sam?
Yeah. As far as I see.
Sam I am?
Sam.
Okay, well, maybe you could say that, but I can't. Okay, so the wiring, let's look at the wiring. Is the wiring between the bulbs in series also? Does it go wire in, comes out, in, out,
Yeah.
through, right? And then if we look at these bulbs, what do you see?
Empty?
Kind of looks empty from here, standard kind of light bulb. What do you notice about the outer surface here?
Yeah, it's like rough.
It's like rough and kind of rubbery, plasticky, right? Now, go over and look at that one that we just used on the screen. And now you can, what does that surface feel like?
It's more glassy. So
It's just straight glass. You can see inside it, right? And when it got with the full voltage, was that comfortable to look straight at that? Ah. Okay, so we have to always be thankful of engineers, right? They realize it's not so comfortable to look at the bulb directly, so they put a light diffuser on the surface. Now let's look at an intermediate one over here. Doesn't this one have a light diffuser?
Yeah.
Now feel it though.
Smooth still.
That's smooth, right? So this one is glass, that one is glass, but for the older style bulb, the light diffuser, the white stuff that's there to help with that so it's not so bright looking directly at it, is on the inside. This bulb has it on the inside. These bulbs have it on the outside. Why? There's an additional feature. You remember when you were a kid and you saw your brother run through the sliding glass door to the patio and broke the glass? Do you remember that? What happens when the glass breaks? It shatters. And those kind of glasses these days are made with a plastic in them, or made to shatter in a way that they don't have sharp edges. The windshields on automobiles have had plastic layers in them for about 80 years now to help reduce the injuries of people hitting windshields. This has just a little bit of sort of white coating on the inside, and the glass breaks, it shatters, goes all over the place. This guy has the white coating on the outside, and when it shatters, it's a little rubbery. We're going to bust one up in just a minute. Isn't it fun to break stuff? Yeah, yeah. Okay, anyway, turn on the lights. Let's see, do we have, yeah, oh, okay. So there's the lights. We've got 4 bulbs in series. Why don't you unscrew one of them? I don't care which. And that's the equivalent of breaking the filament in that one, right? Which causes an open circuit, and so no current can flow. Oh, screw it back in. And if we look at all 4 of them, would you call those bright, dim, compared to what you're expecting for the light bulb? What's the brightness? It's dim, right? So it's less than 100 watts coming out of the, let's see, what kind of bulbs are these? These say 60 watts. So that's the standard, American standard is about 60 watts in a typical bulb. And so those are way less than 60 watts of light and heat being generated, right? Okay, so let's turn that guy off. Now the parallel bulbs, are they in parallel?
Yeah.
They have the same physical appearance of being in a line, of being in series, but the wiring is in parallel now, Sam has confirmed. Yeah, good job. Okay, let's turn these lights on. Whoa! Turn off, turn off. Check to see if it's too hot to touch. Is it okay?
It's kind of warm, but
Kind of warm. Unscrew one. I know. Thanks. So, okay, it's unscrewed. Now turn back on. Oh,
Should I screw it back in?
go ahead, go ahead. Okay. So having one of them go open, go ahead, turn it off, it's too bright. One of them go open didn't affect the other three, did it? In particular, we also notice when one of them went open, did the other three get brighter? No. I don't think so. Let's go try it again. We have one descent. Let's do it again. Let's measure it again. Turn them on. Okay, turn it off. No, okay, we want to do it where, okay, go ahead, turn it on.
It's okay.
Go ahead. Did they get brighter or not? No. Okay, turn it off. Okay, screw back in. Okay, so, and what was the approximate brightness telling you? Was that about 60 watts per bulb? That was about normal brightness, right? So these guys in parallel were seeing the full voltage. The guys in series were seeing 1/4 of the voltage per bulb. 1/4 of the voltage, quarter of the voltage. V squared is what then? 1/16. 1/16 of the power per bulb times 4 bulbs. We're not getting much light that way, are we? It's mood lighting. Okay. Series and parallel. Does the excitement continue?
Wow.
Let's do this one over here. Why don't you describe what you see?
Okay, it's
Let's go bring the wire in
yeah,
here.
the wire goes in
and
to the top one,
to the top one.
and it goes down and separates into two.
Goes down and separates into two. So this top bulb is said to be in series with the bottom bulbs, and the bottom bulbs are parallel to each other. So we have a combination of series and parallel going on here. So whatever current flows in the circuit, all of it will go through the top one. But the current will then split and go through the two on the bottom, providing they're both plugged in, right? So the current splits here means these guys will have half as much current each, if they're each 60 watts, half as much current, 1/4 as much power as the guy on the top. Then the next thing we would observe would be, what happens if Sam unscrews one of the bottom bulbs?
These two
Then,
will stay lit.
yeah, but this guy is going to carry all the current?
No, just the same.
Okay, and we have to think about the total resistance in the circuit is changing too then. Okay, let's go ahead and turn it on. Oh, the guys at the bottom, can you see them?
Yeah.
Right? They're a dim bulb today, aren't they? Okay, why don't you unscrew one of them? Oh, I didn't hear you guys. The next one, we'll do that together, okay? The excitement. They're helpful, aren't they? Yeah,
They're good people.
they're good people. Okay. All right, that's, what's the next one say?
Series parallel.
Let's try this one. Go ahead, this guy.
So opposite of that?
I don't know. It kind of looks like it's upside down, doesn't it? Okay, unscrew one of them. Turn that one back in. Unscrew the other one. No, oh, okay, fine. Okay, now try this guy. Oh, I don't know. What do you think?
Shouldn't this one light up?
Okay, so what do we have here? Now we have, let's turn it off. And can you describe, it's not the same as this guy in a visual appearance, is it? This guy gets the juice, right?
Yeah.
And this guy does too,
Oh, yeah.
right? So it's a different circuit. The voltage comes along at the top and is shared with a single bulb, and then there's two bulbs in series over here that are in parallel with this. So we get different combinations. This one, the one we did first with the triangle of lights, had a single bulb that was in series with two bulbs in parallel. Now we have a single bulb that's in parallel with two bulbs in series. Repeat that quickly. Okay. So Sam shuffled series. We got to come up with a tongue twister with that. Okay, we got one more to do here, don't we?
Yeah.
Uh-oh, series parallel. Heavy lifting, one more heavy lift. Go ahead. Okay, we got all the lights on. Now, try unscrewing one, see what happens. Go ahead. Doesn't matter which. Okay. Unscrew a different one. Okay, so we see what we have here is 4 bulbs, pairs in series, and overall each pair in parallel. Okay? And we notice it's not so bright. Again, because the voltage is shared between 2 bulbs. 110 volts is going across 2, so it's only 60 volts per bulb instead of the full 120 volts. Okay, Sam, let's turn that off. And now the excitement, the excitement. Let's take a look here at one of these bulbs. So this bulb is one of these guys. Well, let's show them it works. Put it in somewhere. Okay, so it works, right? Okay, now the resistance of this thing is something you could calculate as being the resistivity times its length divided by the area. And the resistivity depends on the temperature. The resistivity changes as the bulb warms up. But what I'd like you to do is we're going to have Sam break this bulb open. So just take the hammer, do it in the middle here, try not to hit anything else, and just give it a little smush. And just be gentle, kind of like cracking an egg. We'll work it open a bit. Okay, yeah, good. Now, why don't you claw about at it, but make sure that no glass is going to cut you, okay? Just open her up with that claw. Okay, let's keep moving the glass away and try not to hit the filament. Can you see the filament now?
Yeah.
Okay, so there's a filament in there, right? And what, do you want to do some of the, here, let's break a little more off. Ben, when you take this, there are a lot of little tiny pieces, very small, okay? All right, so there's the filament in the middle. Does it have a big loop like the one that we had on the board projector? It doesn't, right? It's kind of more or less almost a straight line, but it's a little tiny coil, isn't it?
Yeah.
How thick is the wire?
Oh, I don't know.
What could you compare it to?
A couple strands of hair.
Couple strands of hair, maybe? So now you know how thick the wire is, right, for the diameter. And the coil makes it be a little longer length in this same distance, doesn't it? So if you stretched out the coil, about how long would it be? About double what it is?
Probably double.
Double this distance. Okay, so what is that distance approximately?
It would be around 4. Maybe.
Yeah, so it's about 2 centimeters across now. So if we stretch that coil out, it'd be about 4 centimeters long. And the diameter is, so you know L now, right? So and the diameter is about, Ben is claiming about 2 times the thickness of a hair. Or, you're not Ben.
No.
You're Sam.
He's been, right?
Ben's over there. He's a ventriloquist. Okay, so we have it's about 4 centimeters in length, and the thickness is about twice the thickness of a human hair. So you should be able to say what is the resistance of this light bulb from the power dissipation. And from the power, what's the power when the thing is on?
60 watts.
Say that louder.
60 watts.
Excellent, Sam. Okay, been there and done that, huh? So 60 watts, and what's the voltage?
120.
120 RMS, right?
Yeah.
Okay, and so we know the voltage. Doesn't that tell us the resistance from over here, right? If we know the resistance, we know the length, we know the area, you can tell me the resistivity of the tungsten when it's hot. Got it? Are we excited to be able to do that? Yes, we're terribly excited, aren't we? Okay, but this is the stuff that makes the light bulbs up there work for us. So when we're done with the lecture today, I want you to come up here and look at Sam's handiwork. It is literally handiwork, right? And double check his measurements, because otherwise Sam may have lied to all of you so that he'll be the only one to get the exam problem right, if I put it on an exam. And he's counting on getting good notes from you guys, and you know he's lying up here, so you've written bad notes so that he won't get it right. Yeah? Okay. All right. Thank you, Sam, very much. Excellent, excellent demo stuff. Okay, now let's expand our ideas here just a little further. Okay. The resistors cannot store charge, can they? So if the resistor can't store the charge, it had to go by. It came from one place and went to another. But do we have something which can store charge? Something which has the capacity to store charge. We have capacitors. And things that can dissipate energy, like resistors. And we looked at this demo last time, didn't we? So let's think about what's going on here. What's under my hands now? The power supply with some meters on it. This is providing voltage difference. It's a battery in essence. It's providing the voltage difference. Here's a switch that looks like it was designed in the mid-1800s, right? This is a very tiny Frankenstein would use this switch. We'll bring in bigger ones and then I'll do that later. Okay, and then the wires go over, there's a capacitor here and a light bulb. So if we put the switch in one place, it allows the voltage to push charges through the electric field in the wire onto the capacitor. Makes a circuit with the power supply and the capacitor. Pushes the charges. Then, if we throw the switch the other direction, it changes the circuit, removes the power supply from the circuit, and now has the light bulb and the capacitor in the circuit. So we need to come up with some rules about how currents move around circuits and how voltages are distributed, and then we do this again, don't we? Yes, question?
Can you describe that circuit one more time?
Yes, I will. In fact, I'll draw it out for you in about 5 minutes, okay? So, and if that doesn't adequately hit whatever question is in your mind, ask for more then, okay? So let's take a look at some kind of circuit. Let's put a voltage and a resistor. So here's some power supply, and maybe it has some voltage, and we draw it with that kind of symbol. A shorter bar horizontal with a longer bar over it horizontal, in this case, is a battery or a supply of voltage. Electromotive force. So we use this squiggly E for historical reasons, electromotive force. There is drawn here in this rectangle then symbolically wire, which allows the charge to move through the circuit. And over on the other side, I've drawn what looks like kind of a sawtooth, kind of like, oh, imagine a saw. Would you like to slide down a saw? No, because there's a lot of resistance. There's going to be a lot of frictional loss, more than you want, right? So if we draw it squiggly like that, it's kind of representing a difficult path. Maybe think about going up the side of a mountain on all the switchbacks is another way of visualizing it. Okay? So the resistor is over there. Does current flow in the circuit the way I've drawn it? Yes. So current will come along and go this way like this, and we could keep track of it. Since resistors don't store charge, all the current coming along at the top goes through the resistor, comes down along here, and goes back to the power supply. That concept, we are saying that the charge is conserved, so the current must be something we can keep track of in accounting, right? Another thing that we can do here is look at our energy here. We go along from the top over to the resistor. There was no resistance here, so our energy stayed constant going along here. And then we go through the resistor and our energy drops, it's dissipated. We go along back over here to the battery and we're at a lower voltage, and then we get on the elevator in the battery and get pulled back up to the higher voltage. So we know we can keep track of the voltages going around a loop, and if we go back to where we started, we should be at the same voltage. These two concepts are known as Kirchhoff's rules. Kirchhoff's, I guess that's a Russian name probably, but I don't know. So Kirchhoff's rules, that the current going into a junction must come out. The current going into a junction must come out. And we just witnessed that here. Going in was shared and split. And the total current could be accounted for all the time. And the other one is the sum of the voltages around any loop must go back to where you were. So the sum of the voltages have to be 0. In other words, we have an EMF over here. The voltage drop across the resistor is what? I times R. That equals, in this particular simple drawing, must equal the EMF of that power supply. So our Kirchhoff's rules, the sum of the EMFs and voltages drops around a loop is 0. The sum of the current going into a junction of some sort must equal the current going out of the junction. Let's think of where we could have a junction and we'd want to think of that. Let's have now 2 resistors. Here's our EMF, R1, R2, and here's the current. When the current arrives here, let's call that I naught. When the current arrives here, we have I naught, I2, and I1. What we know by our observations here is that I1 plus I2 equals I naught. So conservation of charge and conservation of energy give us Kirchhoff's rules. You can then draw all kinds of fancy circuits, so many that you will fall asleep before you even start to work on them. And you can write down all the equations of the different possible loops. Let's take a look. I could go on this one on a loop through the EMF over here and through R1 and back over to here. Or I could do a loop through the EMF and go along on the outside through R2 and back over. That gets me 2 conservation of energy equations. That would tell me, for example, the EMF drop is equal to I1 R1, and by going on the other loop, I also know the EMF drop is equal to I2 R2. There's another loop we could take. We could go a loop right through here, just through the resistors that are in series there. There's no EMF there, is there? There's no battery there. What that says is that going up the hill here on the R1 must equal going down the hill here on the R2. We know the voltage drop across them must be equal. So these are different ways to apply these Kirchhoff's laws. Let's take a look at a little more complicated circumstance where we do it with a capacitor in here as well. Let's start by putting the, let's see, we had Sam helped. Okay. Oh, who has not helped? You've helped, you've helped, you've helped, right? Have you helped? Oh, this could be your moment. Would you like to help? Okay. Have you helped? I think you did already, right? Yeah, you've helped, yeah? You've helped. Okay. It was your lucky day. Hi, I'm Roger McWilliams.
Cecilia.
Cecilia, pleasure to meet you. Okay, Cecilia's with us here, and she's going to help with the power supply stuff here. Let's see if I turn this guy on. Now, what we're going to do to start, I'm going to draw a circuit, and then I want you to see if you agree with it by just looking at things. It'll be a little hard for you to tell because you're not quite used to looking at those things, probably. Now we're going to look at some time-dependent things. So let's have an EMF. I'm going to put an open spot on the circuit, and then over to here. Oh! At the start of next lecture, if I don't remember, please tell me to do the capacitors in parallel and capacitors in series so that we understand the physics of that, okay? I intended to do it right after that and slipped a bit. Okay, this is a capacitor. This is our EMF, and this is a switch. So what I want to do with Cecilia is, here's the switch. You can see it. It's this thing. And here are the two wires coming out of the power supply, right? Let's see. So what we're going to do is throw the switch to charge the capacitor. Here's where the power comes in. We need it to go here, right? Like that. See how, if I move this guy, you move it over here. Pull it towards you. There you go. See how now it goes here, through the switch, down to there, and over to the capacitor, right? On both sides, right?
Yeah.
Okay, so right now what we're doing is charging the capacitor. And except that it's not, well, let's make more voltage. We could do this one. I think we could do 100 volts on this guy. Let's find out. Okay, so, or no, what's the voltage say? I can't read upside down very well.
It's going to 75.
75, maybe it'll get, okay. So we're going to go 75 volts. Current. What the heck? Let me just check something. Okay, that worked great. Okay, so what we're doing is charging the capacitor. When we throw the switch, now we can put, there is going to be some time-dependent charge on this capacitor. Initially, before we throw the switch, how much charge is on the capacitor? 0 if it was shorted out. So let's think about starting with it being at 0, okay, Cecilia? That's what we're going to go for, 0. And now we we close the switch. The voltage on the capacitor and the charge on the capacitor, what's going to happen? Initially, let's think about the capacitor. Is there any charge here to start with? No. So when we close the switch, that voltage is completely across there. Oh yeah, let's push lots of charge onto the capacitor. So the charge will build up very quickly to start. And the voltage will build up very quickly to start. Because the current can be fairly high. So we can have the current on the capacitor very high and dropping down. As we get more charge on the capacitor, Now that charge is there, and saying to the next little bit of dq to bring in on the current is going to have to not have the full voltage across to push it in. So as we get more and more charge there, it's going to be less and less push over here to get more charge onto the capacitor. So the charging slows down. What kind of curve does that look like? Doesn't that look like an e to the minus t over some kind of time, an exponential decay? Okay. Now, let's go here and dissipate. What we're going to do now is a different circuit. Here's our capacitor. Now our switch is going to go, instead, we're going to have this circuit. We've got a C and an R. Capacitors store charge. Resistors dissipate the energy. When we close the switch, what's going to happen? We close the switch, current can flow. We're going to have a voltage across the capacitor, right? We have the voltage on the capacitor. What's that voltage equal to? Let's see. We think about capacitance is the ability to store charge. So the voltage is Q on the capacitor divided by C. The rate at which that charge leaves is the current. Over here, the voltage across the resistor is going to be I times R. That's equal to dq dt times R, which is the rate at which the charge is leaving the capacitor times R. So initially, the charge on the capacitor is very large. Let's see what happens. The charge on the capacitor is very large. Push it this way to close it. And what happened? When was it brightest? At the start. When was the most power being dissipated in the resistor? At the start, right? And then it went down with some kind of curve to it. And the power in the resistor, then the power in the resistor versus time started high and went down like that. As the total charge on the capacitor reduced, as the total charge on the capacitor reduced, what happens to the voltage? The voltage drops, doesn't it? If the voltage drops, what happens to the voltage on the resistor? It drops, so that the total power dissipated in the resistor must drop as the voltage on the capacitor drops. You can see mentally how things are pushing the electric fields in the wires as a function of time by thinking about it that way. Then on maybe the start of our next lecture, maybe we'll just reinforce it by writing some of the differential equations for it. Wouldn't that be exciting? We could do that on Thor's Day, right? The day of power. Okay, thank you, Cecilia. Appreciate it. Very good job. Remember, come up and look at this filament that we've broken open. You need to admire Sam's handiwork.